Hello students, let us continue with chapter 5, Introduction to Euclid's Geometry. In the previous class, we learnt about certain terms such as definitions, axioms, postulates and theorems. So, I have listed down the axioms and postulates that we learnt about. Using these, we will be solving certain examples and our exercise, that would be 5.1. So, to start with exercise 5. The solved examples before exercise 5.1. These examples are on pages 83 to 84 of your textbooks. So, the first question, if A, B, C are three points on a line and B lies between A and C, then prove that AB plus BC is equal to AC. So, let us just draw the line AC and mark the point B on it. I have my line segment AB or line AB, sorry, AC, and B lies in between. Notice that B is not the midpoint or anything, B is just lying anywhere between A and C. So, you need to prove that AB plus BC is equal to AC. So, how are we going to prove that? Let us say proof. Now, we can see that AC, just look, hide this B, you can see that AC is coinciding with AB plus BC. So, according to the axiom here, things which coincide with with one another are equal to one another. So, AC is coinciding with AB plus BC, therefore, it is going to be equal to AB plus BC, that is AC is going to be equal to AB plus BC. Now, let us write this down. We can see that AC is coinciding with AB plus BC. Therefore, according to the axiom, I will mark this as 1. Which axiom? Things that coincide. So, coincide is what? Superimposition. For example, I have one line over here, I place another line, exactly, line of same length on top of it. So, it makes it equal. Like I had discussed in my previous class, I am sorry for the sound. Like I discussed in the class, if I have two chalks of equal lengths, I place one behind the other, one above the other, they are equal length, so the one that is behind will disappear. Like you won't be able to see it, it won't be visible, not really disappear. So, things that coincide with one another are equal to one another. I will mark this statement as 2. So, from 1 and 2 what do we get? From 1 and 2, AB plus BC, or we can, since AC is coinciding, I will just write AC is equal to AB plus BC, which also means AB plus BC is equal to AC, which is what we needed to prove. Therefore, I will say hence proved. Pretty simple, isn't that? So, you just have to use the axioms and postulates to solve these kind of questions. So, without wasting much time, let us proceed to the second one. Prove that an equilateral triangle can be drawn on any line segment. So, what we have to do is, given any line segment, you have to use that line segment to draw an equilateral triangle. How are you going to do that? Let us see. Let us say I take a line segment of 5 units. You can take this as 5 centimeters in your book or any length. Just make sure you mark the length here. And I will name this AB. Now with A as my center and AB as my radius, I am going to draw a semicircle. Similarly with B as center and BA as my radius, I am going to draw a semicircle. Not a semicircle, I am just going to cut arcs like this, so that there is an arc through A from B and there is an arc through B from A, through A from B, and they both meet at a point here. I will call this point C. Alright. Now what I will do is I will connect C to A and C to B. And if you measure this, you will notice that if you measure AC and BC or CB, you will notice that this length is 5 units, and this length is also 5 units. So this triangle is equilateral. So how did we draw the equilateral triangle? We just took a line segment of say 5 units and then you cut arcs. Now you will notice that for this circle, if this was an entire circle, you have this as the radius. Similarly, if you have this as your circle, you have this as the radius, right? So, and the radius is what? 5 centimeters each. Therefore, we have drawn an equilateral triangle using one line segment. So, let us do the construction and proof of this equilateral triangle. So, first construction, I will say draw segment AB of any length. In our case it is 5, so you can just put this in brackets. In this case we have taken 5 units. You can take any length, you can take 5 centimeters, 6 centimeters, 3 centimeters, anything you want. In our case I have taken 5 units, so I have just mentioned it for you. Now with what have we done? What was the next step? With A as the center and AB as my radius, I cut an arc through B, right? With A as center and AB as radius, I am just writing R for radius, cut an arc through B. Then the next step was with B as center and BA as my radius, I cut an arc through A. So with B as center and BA as radius, cut an arc through A. So you will notice that these two arcs are intersecting at certain point. You will name the point C. Name the point of intersection of the two arcs as C. So I have named this point of intersection. Now join A to C and B to C through straight lines, through so once you have joined this, you will say measure AC and BC. So you are measuring. So what do you notice? That the length of AC and BC is the same as 5 units. Now this is what we have to prove. So So you measure AC and BC and write your observation. Remember when we were discussing the introduction, there were always observations and they were reasoned out with actual axioms or derivations. So this is what our observation is. Now we will reason it out. So I have proof AB is equal to AC. Why? Because they are the radii of the same circle. If you see, this is an entire circle over here. Correct? So your this and this, first of all, the circle will be something like this. So AB and AC are the radius of the bigger circle, correct? Similarly, what do I have for this circle now? We have BC and BA as the radius. So of AB and BC. AB is equal to BC. Why? Because again they are the radii of the same circle. So now using our axiom, the first one over here, things which are equal to the same thing are equal to each other. What can we say? Now AC and BC are equal to AB. Both of them are equal to AB. Therefore, we can say that AC and BC are equal. Therefore, we can say that AC is equal to AB, which is equal to BC. You can write it in any order. So, I will say using axiom, things which are equal to the same thing are equal to one another. So I'll mark this as 1 and I'll mark this as statement 2. What do I get? From 1 and 2, AB is equal to BC, which is equal to AC. Therefore, triangle ABC is an equilateral triangle. So what have we done in this sum? Using any line segment of any unit, in our case we've taken 5 units, we have drawn an equilateral triangle. So there is a note to mention, two circles, Euclid had proved that two circles drawn with centers. He had not proved, actually he had just assumed without proving that two circles drawn with centers A and B will meet each other at a point. So this is what we have done here as well. Two circles with, so this was in one circle, correct, and this was another circle. So they had different centers. Now two circles with different centers, they are meeting at a point C. Alright. So this was about the solved example. Let's go ahead and solve this theorem on page 85. Before I do that, let's erase the board. Okay. So two distinct lines cannot have more than one point in common. We need to prove this. So in order to prove this, what we will do is we will assume that there are more than, we will assume that two distinct points do have more than one point in common, and then let's see how we proceed. So I'll say proof, let the two lines be L and M and let them meet or let them intersect at 2 points P and Q. Correct? So according to this, what will we have? We will have two lines passing through two distinct points P and Q. Therefore, this implies what? Two different lines are passing through two distinct points. But now let's take a look at postulate 1. A straight line may be drawn from any one point to any other point. For proving postulate 1, we had taken into consideration axiom 5.1, which says that according to axiom 5.1, what does it say? Given two distinct points, only one unique line can pass through these 2 points. So I'll just write it down. Given two distinct points, there is only a unique line that passes through them. So I'll mark this as point 1 and this as statement 1 and statement 2. So if you notice, 1 and 2 are contradicting each other. So which obviously now axioms are considered to be universal truth. So universally true. So obviously this is a valid point and this is not a valid point. It's an invalid point. So obviously our assumption is wrong. So I'll say 1 and 2 contradict each other. Two is valid since it is an axiom in brackets universal truth therefore our assumption is invalid. Hence you are going to write the statement, hence two distinct lines cannot have more than one point in common. Hence we have proved our theorem 5.1 on page 85. Let's take a look at the first exercise, that's 5.1 in the next class. Thank you.
Hope this video increased your knowledge. For more such videos and a completely free educational content, log on to www.epathshala.org or visit our ePathshala YouTube channel. We have each and every question solved for maths, physics, chemistry and biology. So subscribe our channel, share with your friends, like our Facebook page and follow our Twitter handle for regular updates and important educational tips, and also win ePathshala goodies. So what are you waiting for? Subscribe this channel and enjoy the freedom of education.